Alright, so in this video I'm gonna be explaining this important paper with the title Cayley graph propagation. This paper in 2023 in the Journal of Symmetry and Geometry Neural Representation by DeepMind. In spite of a plethora of success stories with graph neural networks and modeling graph structured data, they are notoriously vulnerable to oversquashing, whereby tasks necessitate the mixing of information between distance pairs of nodes. To address this problem, prior work suggests rewiring the graph structure to improve information flow. Alternatively, a significant body of research has dedicated itself to discovering and pre-computing bottleneck-free graph structures to ameliorate oversquashing. One well-regarded family of bottleneck-free graphs within the mathematical community are expander graphs. Of course, I've explained this I've explained expander graphs in playlists for spectral graph theory. It is very related to this topic of oversquashing because naturally it creates a graph that doesn't have the problem of oversquashing because you can jump for example, from this node, if you want to travel from this node to a very far distance node, then there with very few hops, because of the nature of that expander graph, with very few hops you can move there, so there is no problem. So the nature of this expander graph makes it possible so that you can go with very few hops. So in this work, we show that truncation is detrimental to the coveted expansion properties. Instead, we propose CGP, a method to propagate information over a complete Cayley graph structure, thereby ensuring it is bottleneck-free to better alleviate oversquashing. So, expander graph is categorized by its unique properties of being both sparse and highly connected with the number of the edges, scaling linearly with the number of nodes. Due to the definition of an expander graph, there are consequently several known construction approaches. We will focus on the deterministic algebraic approaches, that is in this reference 13. A family of expander graphs have been pre-computed, leveraging the well-known theoretical results of special linear groups, for which a family of corresponding Cayley graphs can be derived. And the oversquashing problem is an old topic, whereby the information of a message-passing neural network is aggregated from too many neighbors, meaning as a consequence they are squashed into a fixed size vector. This can result in loss of information. This phenomenon was then formalized in these references, showing that the Jacobian of the node features is affected by topological properties of graph, such as, for example, there are some papers that use Ricci curvature. Also, there are some papers that use effective resistance to deal with this topological problem. Of course, in comparison to oversquashing, oversmoothing is well understood, easy to deal with. You think even drop message, drop nodes, those papers are good enough. So that's why graph wiring is is very attractive, but there is a risk. If you just do rewiring whatever you want, then if you don't respect that you're changing the graph topology, then your generalization will be very poor, because you shouldn't change the topology of the graph. If you change the wiring, then it becomes a totally different topology. So we should be aware of this problem. Then here they talk about expander graph-based rewiring, which is a very secure way to do graph rewiring. Because as I said, expander by its nature provides us to walk from one node to any node with very few hops. And that is the real motivation of papers like this that use expanders. Now let's focus on the Cayley graph expansion. The structure of a Cayley graph makes it an ideal conduit for the propagation of information due to its sparsity and being highly connected. In particular, the family of Cayley graphs derived from this Cayley are in a magnitude of order of cardinality of V to the 3 and are well known to have high spectral gap. So, however, this still should be a hard problem, so they opt to implement a greedy strategy, and it imposes a costly pre-processing. One metric to measure graph connectivity is the coveted Cheeger constant. I have explained Cheeger in playlist for spectral graph theory. Also, papers for Chung in that playlist. That we have a lower and upper bound for this Cheeger, and that is related to the first eigenvalue, which is very exciting. The second smallest eigenvalue, or spectral gap of the normalized graph Laplace. The diameter of the graph influences the effectiveness of traversal between nodes. A lower diameter facilitates a more efficient graph structure. And then they do this Cayley graph propagation. So this construction requires us to add new nodes to the graph. Hence, we need to modify the feature matrix into an extended version. Because EGP makes advantage of both input graph and the generated Cayley graph, we can also appropriately extend the original adjacency matrix to incorporate new nodes. So we construct such a tilde that it adds self-edges to the virtual nodes only. Now for a two-layer, we can have such a graph neural networks, but now with a tilde and A of Cayley. Your choice of graph neural network could be anything, but you can also use graph isomorphism network as a choice. And finally, they did some tests on different data sets. For example, for MUTAC, they compare it with different approaches, different models. So the colors highlight first and second and third. OOT indicates out of time for pre-processing rewiring time. You see that results using Cayley graph in different layer approaches compared against FA on the two dataset. Two dataset is you can find it in PyTorch geometric. That's why you can access all these datasets.